In many nations, electric power requirements are increasing rapidly. Generation of power from coal, oil, and water resources will continue for many years. But nations faced by high energy costs and other problems are already taking steps to use the new alternative, nuclear power generation. Nuclear power reactor technology, developed in the United States by the spring of 1958, may be useful to many nations. You're about to see the pressurized water and boiling water reactors, which are already available for practical electric power generation. And then the homogeneous, organic moderated, sodium graphite, and fast breeder reactors. A major development program is being carried forward to advance further the technology of these and other systems in order to obtain better fuel use, higher performance, and lower costs. Before an experimental power reactor could ever be built, a sizable body of fundamental data had to be developed for every aspect of reactor technology.
Theoretical work required years and was based on studies by scientists of many nations. High-speed computing machines have been used to calculate flux distribution patterns, thermal utilization, and interactions under conditions of nuclear reactor operation.
Reactor metallurgy requires an investigation of the first magnitude to develop fuels, alloys, and other materials with properties satisfactory for the environment of reactor systems. Special high-flux reactors were built to obtain physics and engineering data on the performance of design models, fuels, and other materials. Tests in these machines reveal the effects of radiation on the properties of materials.
2 to 3 years of testing are required to develop a new material such as an alloy of zirconium, which has the advantages of stainless steel with only a fraction of its neutron absorption cross-section.
The nuclear power and equipment industry is developing facilities for fabricating and testing fuel elements, manufacturing reactor cores, developing and providing a wide variety of components and services.
The industry is continuously expanding its facilities. In the United States, the first plant to demonstrate a power reactor concept on an industrial scale was the shipping port pressurized water reactor, built by the Westinghouse Electric Corporation. It has a heat output of 231,000 kilowatts, a steam pressure of 600 pounds per square inch, and a design capacity of 60,000 net electrical kilowatts. Though industrial power will be produced, the shipping port reactor is essentially an experimental tool to further the development of large-scale power reactors.
The reactor core is a lattice of highly enriched plate-type assemblies surrounded by a blanket of natural uranium rods. The primary cycle consists of a single reactor heat source and 4 individually shielded coolant loops to circulate the light water moderator coolant. Each loop flows through a separate heat exchanger with its own steam generator. A pump completes the cycle. One loop can serve as a standby alternate for maintenance. The primary coolant system is connected to a pressurizing vessel which maintains proper pressure limits in the reactor. In the secondary plant cycle, low-pressure saturated steam enters the first stage of the turbine, passes to an external moisture separator, re-enters the turbine, and finally exhausts to condensers. Then on to feed water heaters, where the temperature is raised by the exhaust from the separator. A boiler feed pump completes the circuit.
A full-scale working model of the shipping port reactor was operated for nearly 3 years at a power level of a few watts to check analytical calculations and develop some of the reactor physics data required.
Fabricating shipping port components, like the 160-ton pressure vessel, required major industrial facilities and skills. Machining problems included closer tolerances than had ever been required on parts this large. The scale and precision of the reactor's pressure system provided the opportunity for many private industrial firms to gain knowledge and experience with reactor components. Because of the experimental nature of this reactor, flexibility was a requirement of many components. The closure head of the pressure vessel has 10 ports to permit changing or rearranging fuel elements, and others for instrument leads or control rod drives. Reactor components require material integrity and manufacturing precision of the highest order.
Reactor plant containers for the coolant loops and auxiliary equipment were assembled in position, then sealed and tested. The containers are designed to prevent escape of any radioactive gases or materials that might be accidentally released as a result of major plant casualty. System components were installed through access openings provided in the pressure containers. 2 steam generators are installed in each of the containers adjacent to the reactor. As a final safety measure, the entire nuclear portion is enclosed in concrete. The low-pressure 1800 RPM turbine and the generator were installed while the nuclear portion of the plant was being completed. The core was assembled in its cage enclosure at the reactor site. The 113 blanket sub-assemblies use 14 tons of uranium oxide fuel. This particular core geometry is expected to yield about 50% of its power from the seed assemblies and 50% from the blanket assemblies, including a small amount from the fissioning of plutonium. Special equipment was developed for precise handling of the core and other components in the reactor vessel. The system is designed to contain the light water primary coolant at 2,000 pounds in order to prevent boiling during steady state operation. The first core is expected to provide significant data on the questions of long-term reactivity and fuel life. The entire plant was designed to accommodate a higher-powered core in the future.
High-purity light water coolant flows upward between the fuel and rods. The heated water flows from the upper part of the vessel to the intermediate heat exchangers and steam generators. On the return cycle, a small percentage is bypassed for purification. The reactor is largely self-regulating due to its negative temperature coefficient, an inherent control parameter in a system of this design. For example, a drop in demand for generator load lowers the turbine steam requirement. Hotter water returns to the steam generator, which means hotter coolant water returning to the reactor. As the reactor heats up, reactivity is reduced, which in turn automatically reduces the reactor power level to match the lower load demand.
After extensive testing of components, fluid, and control systems, Shippingport went critical early in December 1957. After additional testing to assure proper and safe operation of the reactor and steam plants, Shippingport went on the line later that month with 60,000 kilowatts of electrical capacity to take its place in the industrial power network of the Duquesne Light Company. The reactor is stable and responds almost immediately to load demands. In the immediate future, Shippingport's contribution to reactor technology will affect its operation more than any requirement for its power. Shippingport will provide valuable experience with heat utilization, system leakage and maintenance, and other problems. Basic information on technical and economic questions to benefit the design of future industrial reactors. A further application of the pressurized water concept is the Army Package Power Reactor at Fort Belvoir, Virginia. All its basic components can be transported by air. In full-time service since July 1957, the plant has operated continuously with no machinery failures. The reactor was shut down temporarily for a routine inspection of the turbine and conventional plant equipment. When activity in the containment shell has reached background level, the water filling the access tube is drained. Inside the containment shell, only a routine inspection is performed. Penetration of the reactor shield tank is unnecessary. Only conventional equipment needs routine maintenance. The nuclear portion has been so carefully designed that maintenance between fuel changes is not required.
After inspection, reactor startup begins. When the reactor is up to power, the generator is brought online to feed into the Virginia Electric Power Company network. The reactor automatically increases output to meet demand. As an additional test of the reliability of the reactor, the load on the generator is dropped instantly from a full 2,000 kilowatts to the station load of 200 kilowatts. Reactor power level drops to meet the new load and stabilizes itself. Control rod adjustment is not necessary. The reactor is presently demonstrating the usefulness and reliability of small capacity stations.
At Indian Point near New York City, the Consolidated Edison Company is financing the construction of a pressurized water reactor generating station. It will serve as a commercial base load plant to produce a part of the electricity for the network serving the New York City area.
The nuclear portion of the plant is inside a large span concrete shield and carbon steel containment shell. The pressure vessel is enclosed in a water shield tank. The core is an internal thorium thermal converter. The fertile thorium oxide is mixed with U-235 oxide, formed into pellets and loaded in rods. As fissionable U-233 is formed from thorium, it will supplement the U-235 base fuel.
Core development is being performed by the Babcock and Wilcox Company at Lynchburg, Virginia. Major studies with a critical mock-up of the core deal with the behavior of thorium oxide in combination with uranium oxide. The initial fuel loading for the Indian Point reactor is expected to last 20 months. In-pile irradiation test loops are being used to investigate fuel element properties, radiation damage, and the suitability of fabrication techniques.
The schedule for fabrication and delivery of components is closely coordinated with site construction. Inspection and quality control methods include the use of a 2 million volt X-ray unit.
The reactor will produce 163,000 electrical kilowatts. Oil-fired superheaters are included in the steam circuit to raise the steam temperature from 450 to 1,000 degrees and increase the plant's net electrical output to 255,000 kilowatts. The Indian Point station is scheduled to be operating in 1960. With research and development assistance from the Atomic Energy Commission, a group of 12 public utilities are financing the Yankee Pressurized Water Reactor Plant, which will produce 134,000 electrical kilowatts at Rowe, Massachusetts.
Major investigations in progress for the Yankee station include hydraulic flow tests with fuel assembly models, the problems of injecting boron into the reactor coolant stream as a safety control, and the methods for subsequent cleanup by chemical, ultrasonic, or other means. The Yankee plant is scheduled for 1960 operation.
The first complete boiling reactor plant in operation is the experimental boiling water reactor at Argonne National Laboratory. It went critical in December 1956. Although it was designed for a high degree of experimental flexibility, its initial operation produced 5,000 electrical kilowatts. It regularly supplies a substantial portion of Argonne's daytime power needs, in parallel with other generating plants in a local utility network. Its reliability compares favorably with conventional stations.
The light water moderator coolant flows by natural convection. Bulk boiling begins about halfway up the slightly enriched plates in the fuel channels. An outstanding feature of a boiling water reactor is its inherent safety. Any sudden increase in reactivity will result in more steam bubble formations, a less dense moderator, and an immediate stabilization of reactor power at the new level. Steam at 600 pounds pressure flows through a dryer, directly into the turbine, then back through a condenser to the reactor. To compensate for rapid fluctuations in load demand, an automatic steam bypass valve maintains constant steam pressure in the reactor system until the control rods readjust the reactor's power level. Auxiliary shutdown is provided by a high-pressure boric acid injection system.
The core structure can accommodate up to 148 fuel assemblies for experimental variation of core loading. 8 of the fuel elements are of natural uranium. The other 106 are enriched to 1 44/100% in uranium-235. To provide for achieving at least a 1% burnup, the uranium fuel is alloyed with a small quantity of zirconium and niobium. The alloy provides strength, corrosion resistance, and irradiation stability. During the core loading operation, neutron flux and density were continuously monitored. After each loading, there was an attempted approach to criticality. As a safety precaution, the core vessel was sealed with hold-down beams attached to vertical steel columns. In the unlikely event of an explosion, the beams would direct the force downward and leave the upper containment shell intact. In its program of experimental operation, the system has demonstrated its ability to meet changing load demands with a high degree of stability. The meter on the right presents total steam flow. The one on the left indicates the amount of steam going through the bypass valve. The difference in readings is the amount going through the turbine. No appreciable contamination of the turbine or other components has been experienced to date. The level is only slightly higher than background. During reactor operation, routine inspection and maintenance are performed throughout the plant on each shift. The low pressure system made it possible to use many conventional pumps, valves, and other components. Leakage problems have been largely eliminated.
For decontamination studies, sodium salts are dissolved and pumped through the system. Special taps condense steam samples from various points in the system. These samples give an accurate measurement of how much contamination would be carried into plant components if a fuel element ruptured. Future tests will include the deliberate rupturing of a fuel element in order to gain more precise information. One of the basic tests consists of varying reactivity at different frequencies and observing resultant flux variations. Amplitude changes as frequency changes. The data is analyzed for fundamental feedback effects. Results of these studies make it possible to predict stable performance at higher power.
The plant originally produced 5,000 electrical kilowatts from 20,000 kilowatts of heat. This plant, like the other reactors in the United States, is conservatively designed. In December 1957, using the original core with no modifications to the system, reactor power level was increased to 50,000 kilowatts of heat. And in March 1958, power was further increased to 62,000 kilowatts. This can result in a significant reduction in cost per installed kilowatt. Steam produced in excess of that needed to generate 5,000 kilowatts of electricity has been dumped to condensers. Installation of a forced circulation system is planned. Following this change, reactor stability is expected to improve, and the core power density can be increased many-fold. Stability of operation with forced circulation will be compared to that with a natural convection system. The boiling water reactor concept is sufficiently advanced now for commercial application. Future test programs are expected to operate with heavy water and extend the technology even further in the direction of large, safe, and economical commercial plants. At Pleasanton, near San Francisco, California, the General Electric Company has financed and built advanced research and development facilities, including the Valicitas Developmental Boiling Water Reactor. Originally designed for an output of 20,000 thermal kilowatts, the reactor power was increased to 30,000 thermal kilowatts in January 1958. This reactor is a prototype for testing fuel and operating features of commercial-size reactors, such as the Dresden plant. Its flexibility includes both natural and forced circulation, single and dual cycle operation. A private utility, the Pacific Gas and Electric Company, has connected a 5,000 kilowatt generating plant to the reactor, gaining further experience with direct coupling of a reactor and turbine. The electricity is fed into the utility's power network. At Dresden, Illinois, south of Chicago, the first large-size commercial boiling water reactor is being constructed by the General Electric Company for the Commonwealth Edison utility system serving the Chicago area. Research and development for the project were financed by 7 independent private utility companies and an architect-engineer firm.
Dresden will produce 180,000 kilowatts of electricity. At the Atomic Power Equipment Facility of the General Electric Company, a 60-foot high test facility incorporating a mock-up of the Dresden pressure vessel is used to simulate various conditions, including heat and water circulation, as well as the refinement of refueling equipment and procedures. Here also, fuel element materials and designs are tested for void distribution, steam slip, steam blanketing, and heat transfer characteristics.
In the main building, fuel for the Dresden core is manufactured on an assembly line basis. Rod-type fuel element fabrication begins in the powder processing room, where uranium powder is mixed with binder and milled, formed into pellets, sintered, machined to size, welded into tubes, inspected and tested. After testing, the tubes are ready for assembly into bundles and shipment to the reactor site.
Construction of the Dresden station is expected to be completed for pre-operational testing and criticality in 1959. Regular operation is scheduled for June of 1960. In order to avoid the difficulties of fabricating, inserting, removing, and reprocessing solid fuel elements, which are inherent in heterogeneous reactor systems, a long-range program has been undertaken to develop reactors which could use a circulating homogeneous fluid fuel and heat transfer medium to simplify refueling and reprocessing. However, under reactor operating conditions of radiation, high temperature and pressure, there have been many problems to overcome, including severe corrosion. The homogeneous reactor experiment number 1, constructed at Oak Ridge National Laboratory in 1951, was the first experimental power reactor to combine fuel with a moderator coolant. It was operated as a large-scale engineering and physics experiment. Highly enriched uranyl sulfate in solution with ordinary water circulated through a single region core vessel where the fissile material reached criticality. This full-scale plastic model of the core was instrumented to study the hydrodynamics involved at various fluid densities and pressures. Bubbles simulate the radiolytic gases produced by decomposition of the water and fission product gases which form in such an aqueous system.
In the first experimental homogeneous reactor, the stainless steel core was surrounded by a reflector shield of circulating heavy water. A helium pressurizer absorbed surges from load changes. In operation, the uranyl sulfate, at a pressure of 1,000 pounds per square inch, left the core at a temperature of 482 degrees Fahrenheit, flowed to a heat exchanger, and returned to the core through a canned motor pump. A steam drum and generator complete the heat utilization circuit. Reactor power level was controlled by steam demand. The fissile material was returned to the fuel storage tanks, where fuel concentration was controlled. Potentially explosive quantities of hydrogen and oxygen gases pass through a flame recombiner, catalytic recombiner, cold traps, and activated charcoal fission gas absorber. Harmless waste gases were vented to the atmosphere. The deuterium cooler, storage tanks, and circuit completed the homogeneous reactor system. Heavy shielding surrounded all components in contact with the highly radioactive gases and uranyl sulfate fuel solution.
During 2 years of successful experimental operation, many changes and modifications were made. Due to the inherently high negative temperature coefficient, nuclear stability was maintained and power could be increased from 30 watts to 11 megawatts in 1 second and returned to 1 megawatt in 1/10 of a second without damaging the equipment. However, under normal operation, power changes would be undertaken more gradually. The first homogeneous reactor experiment, with its loosely stacked shielding blocks, was dismantled early in 1954. It demonstrated the behavior and stability of fuel solutions, the ability to attain and maintain leak tightness in a high-pressure system, and safe handling of hydrogen and oxygen produced by radiation decomposition of the water. It proved that mechanical control rods are unnecessary and established direct dependence of the reactor's power on turbine demand. A second homogeneous reactor experiment with a 2-region reactor has been constructed and operated to test engineering feasibility and advance the technology of the homogeneous reactor concept. The principle of operation is basically the same as that in the first homogeneous reactor, with the addition of an integrated chemical processing plant.
A cooling coil surrounds the carbon steel blast shield, which contains the double region reactor, a carbon steel pressure vessel lined with stainless steel, and the zirconium alloy core vessel. Control rods are not necessary for this system. In operation, fully enriched uranyl sulfate in heavy water solution passes through the core at 2,000 pounds pressure. Diffuser screens provide a smooth expansion of flow. During initial operation, heavy water will circulate through the blanket. With some modification, fertile materials may be introduced to demonstrate a breeding cycle.
The inlet or diffuser section was formed of plate. The first section has a 30-degree angle. Perforated plates are arranged in the conical section to distribute the inlet fluid uniformly. The top half of the tank is a hemisphere. Oxygen-free welding of the curved surfaces required a number of equipment modifications. The completed core vessel and associated components for handling radioactive fluids are located in the main reactor cell, which will be covered with concrete shielding slabs. The shielding assembly also provides a barrier against the escape of any gases which might result from a system leak. Chemical processing of reactor fluid takes place in an adjacent shielded cell. It is controlled from a separate control room. The system is brought to operating pressure and temperature with no uranium in the system. Then the uranyl sulfate solution is injected to bring the reactor up to criticality concentration. Average core temperature in the reactor is controlled by varying the amount of uranium. The power level automatically adjusts itself to the load demand. This reactor has encountered various difficulties which have caused delays. However, the reactor achieved criticality in December 1957. In April 1958, shortly after its operating power level had been raised to its full design power of 5,000 thermal kilowatts, the reactor was shut down because instruments indicated that fuel from the main core system was transferring to the blanket heavy water system. Further work proceeds to overcome these difficulties.
Concurrent studies are underway to develop a thorium oxide slurry for breeding use in the blanket region. Manufacturing processes being developed include the production of thorium oxide particles having desired properties. Using different concentrations, the viscosity and engineering performance of various slurries are measured. A blanket system mock-up similar to this model is used to study the behavior of slurry particles under different system temperatures, pressures, and velocities.
It is expected that present problems will be overcome and that homogeneous reactors will be able to attain their potential. At the National Reactor Testing Station, the Organic Moderated Reactor Experiment, conducted for the Atomic Energy Commission by Atomics International, went critical for the first time in September 1957. Operating temperatures will range from 500 to 700 degrees Fahrenheit at a system pressure of 200 pounds. Standard hardware and construction materials are used throughout the system. Operating at high temperatures and low pressures, this reactor is serving as a testing laboratory to study characteristics of the commercially available terphenols being used as the moderator, reflector, and coolant.
The organic material is melted, then fed through an expansion tank into the reactor. The coolant flows up from the bottom plenum between the plate-type fuel elements to the pool, which forms a biological shielding above the core of the reactor. Then on to an air blast heat exchanger. A continuous purge of nitrogen over the surface of the organic coolant prevents buildup of hydrogen and light hydrocarbon gases. These decomposition gases are diluted, then exhausted through a stack. The organic is slowly damaged by irradiation. Small quantities are bypassed to a still, which separates the high boiling materials thus formed and returns the organic to the main system. Waste is pumped to a storage tank.
Test instrumentation provides information on the operation of the reactor heat transfer properties, and heat rejection rates, as well as behavior of the organic under the varying conditions expected of a power reactor. Measurement of surface temperature of the fuel plates can detect a buildup of a polymer film from decomposition of the organic. Techniques for removing the film, if it should form, are being developed. Sample taps are provided to obtain specimens of the coolant and gases from various points in the system for laboratory evaluation of the effects of the reactor environment on decomposition and damage. The organic moderated reactor experiment is advancing the technology of hydrocarbon use by establishing data which will be required in the design of power reactors using this high temperature, low pressure concept. An experimental reactor has been built and operated to evaluate the feasibility of molten sodium as a reactor coolant and heat transfer medium. The sodium-cooled reactor concept affords high steam temperature and pressure conditions similar to those of modern fossil fuel burning plants. Low enrichment fuel is used in a graphite moderator. The experiments in sodium reactor technology are conducted and partially financed by Atomics International at Santa Susana near Los Angeles, California. Major studies deal with the life of fuel, control, and safety elements in a system which can produce 20,000 kilowatts of heat with a pressure of only 3 pounds at the free sodium surface.
The coolant is highly radioactive as it leaves the reactor at 960 degrees Fahrenheit. Heat is transferred to a non-radioactive secondary sodium loop and steam generator, which feeds a 7,500 kilowatt turbo generator. A similar auxiliary circuit, rated at 1 megawatt, is operated simultaneously to provide emergency removal of fission product decay heat. To remove contaminants in each loop, a small percentage of sodium is circulated through hot and cold traps. In the sodium reactor core, the graphite moderator is enclosed in hexagonal zirconium cans. Channels through the center of each moderator assembly permit location of the fuel elements in triangular patterns. Additional element channels are provided at corner locations for controls, safety rods, the neutron source, and experimental assemblies.
Each fuel element consists of a cluster of 7 stainless steel clad tubes filled with the slightly enriched metallic uranium slugs. The column of slugs is thermally bonded to the inside of the tube with a sodium-potassium alloy for uniform transfer of heat from the fuel.
To demonstrate the feasibility of coupling a power plant to a sodium system, a single-pass sodium-to-water steam generator was developed. It is enclosed in a stainless steel shell. To reduce the likelihood of a leak and a reaction between sodium and water, the sodium flows past double-walled tubes. Pressurized mercury acts as a heat transfer medium and monitors for tube failure as water flashes to steam in the inner tube. The generator plant was developed and is being operated entirely at the expense of a private utility, the Southern California Edison Company. Overall operation and maintenance of the sodium graphite reactor experiment have been encouragingly successful. On December 20th and 21st, 1951, the experimental breeder reactor number 1 produced electricity from nuclear energy for the first time in the world. This reactor was designed for maximum experimental flexibility to demonstrate the feasibility of breeding in a fast neutron power reactor plant. During the first 4 years of operation, 2 experimental cores were used.
The reactor arrangement for these cores consisted of highly enriched fuel rods, a hexagonal stainless steel separator, and an inner breeding blanket of natural uranium rods. The inner blanket served as part of the reflector geometry. Air-cooled uranium bricks, clad with stainless steel, formed the outer breeding blanket. Sodium-potassium coolant flowed in series down through the inner breeding blanket, then up through the core. Coolant circulates through a heat exchanger at low pressure. A non-radioactive sodium-potassium loop transfers the heat to boiling water in a second heat exchanger. These heat exchanger tubes are nickel, diffusion bonded to copper, with longitudinally machined holes for leak detection gas. Sodium-potassium circulates outside the tube. Water flashes to steam inside. An inert atmosphere is maintained above all free surfaces to prevent coolant contact with air. A cold trap and convection cooling loop for shutdown of the main system complete the circuit.
Liquid metal cooling systems were studied at temperatures ranging from room temperature to 650 degrees Fahrenheit. A conversion ratio of 1 was attained. Other experiments exposed various materials in the reactor's high-energy, high-flux region. In normal operation, the plant was quite stable, reliable, and largely self-regulating. When severe operating conditions were imposed, such as high power at reduced coolant flow, an oscillation in power occurred. On November 29, 1955, an overshoot in power occurred during an experiment in which the coolant flow was deliberately stopped and some safety devices bypassed. This resulted in a partial meltdown of the core. The core was removed and sent to Argonne National Laboratory for disassembly in the inert atmosphere of a hot cell. The molten fuel in uranium, which had alloyed with iron from the jackets, was removed. All enriched fuel was recovered and reprocessed. The meltdown experience provided valuable information on certain safety aspects of fast reactors. A third core was designed to investigate the effect of fuel element bowing on reactor stability. With this Mark III core, bowing can be eliminated or permitted to occur to a certain degree. Stability under both conditions will be studied. Valves have been installed to permit series or parallel flow conditions for the coolant. In parallel, blanket flow can be adjusted to have a temperature rise equal to that in the core. The third core is highly instrumented to detect thermal expansion and reactivity changes. In April 1958, the reactor was brought to a power level of 930 thermal kilowatts. It has already demonstrated the breeding principle and excellent stability under induced oscillations and other extreme testing conditions. The experience is being incorporated in the design of a larger fast reactor, now under construction, to further advance practical power generation with breeder reactors. The second experimental reactor will produce 16,500 net electrical kilowatts and is expected to be operating in 1960.
Near Detroit, Michigan, the Power Reactor Development Company, with associated electric utilities and industrial firms, is constructing the Enrico Fermi atomic power plant to demonstrate the fast reactor concept on a commercial scale. Manufacturing is proceeding on major components such as the refueling device, pumps, piping, and the reactor vessel. Initially, the Detroit Edison Company plans to utilize the Fermi plant's heat output of 300,000 kilowatts to produce 100,000 kilowatts of electricity. After sufficient experience at this level, production can be increased to the generator's capacity of 150,000 kilowatts. Completion is scheduled for 1960.
In this film, you have seen illustrations of work undertaken in the United States by the spring of 1958 to make pressurized water and boiling water reactors available and to develop improved technology for homogeneous, organic moderated, sodium graphite, and fast breeder reactors, which may lead to lower costs. The United States will continue major efforts to advance nuclear technology to help meet the needs of the United States and the other nations of the world. Many significant advances will be made by other nations through their own independent efforts. But to cooperate with other nations and with their professional people, research groups, industries, and governments, the United States will continue to make available technical information, technical assistance, training, fuel, and other materials, as well as processing services and facilities. The United States will welcome further cooperation with other nations in the hope that cooperation to advance nuclear generation will benefit all mankind.